Hello and welcome to video number 20. My name is Atayb Abul Yaman. We're going to go ahead and give a theorem. This theorem is about proving two linear functions as odd. These two linear functions will be perpendicular to one another. We're also going to use these two linear functions to prove or disprove a nonlinear function as being odd or not. So we'll go ahead and start with the hypothesis. The hypothesis is if a function f of x is bisected into two symmetric halves by a linear function LF, then f will have one of three possibilities. F is an odd function if the linear function is g of x equal to negative x. F is an even function if the linear function is the y-axis. And f is neither even nor odd function if it doesn't satisfy any of the first two conditions. So having stated so, we're not going to consider number 2 and 3. We will handle them in a follow-up video. For now, we will just do the first part. So let's get going with the first part. First, we will prove that f of x equal to x is linear. This is the hypothesis. Let the line f of x be defined by the 2 points x comma y and negative x comma negative y. That means f of x connects these 2 points. If f of x is perpendicular to and symmetric about the line g of x equal to negative x, then both functions are odd. That is, f of negative x equal to negative f of x and g of negative x equal to negative g of x for every x in their shared domain. This is the condition that checks if a function is odd or not. So if f of negative x equal to negative f of x for all x in the domain, then f of x is an odd function, and the same conclusion we can make for g of x. Now that we have said so, we're going to go ahead and define d of p1, p2 to be the distance between p1 and p2, and this will be like a short. We will use it if we want to talk about the distance between any 2 points in the xy plane. So let's go ahead and put the xy plane, and also we have the graph for f of x and the graph of g of x. So f of x connects x comma y with negative x comma negative y. Now, to prove that f of x is an odd function, what we have to do is we have to get the slope of f of x. So the slope of f of x, since we have 2 points here, it will be the difference between the y coordinates divided by the difference between the x coordinates. The difference between the y coordinates is y minus y, which will be equal to y plus y, divided by x minus x, which will give us x plus x. So m, the slope, will be equal to y plus y, which is equal to y, divided by x plus x, which is equal to 2x, and that we could be represented by y divided by x. Now that we have m equal y divided by x, we could go ahead and multiply both sides by x, and that will give us y equal to mx. Now y equal to mx, if x is equal to 0, then y will also be equal to 0. And since y is equal to f of x, then when x is equal to 0, y will be equal to 0. That means f of x, the function, passes through the origin. And for sure, the function f of x passes through the origin. Here is the function f of x passes through the origin. Now that we have done this one, we will go ahead and also prove that the distance between x comma y and the origin equal to the distance between negative x, negative y and the origin, and that distance equal to the square root of x squared plus y squared for every x in the domain. We will show what we mean by for every x in the domain in a minute. Let's go ahead and get back to the figure to prove this. X comma y is one of the solutions of f of x, so it's a point that lies on f of x plot. So we're going to go ahead and draw a line that's vertical and perpendicular to the x-axis. So now we will have a right angle triangle, and since we have right angle triangle, then the distance between x comma y and the origin will be equal to the square root of y square plus x square. Likewise, on the negative side of the y axis, we can have negative x comma negative y as one of the solutions of f of x. So we will pull a line up all the way to be perpendicular to the x-axis, and by then we will have made another right angle triangle. This right angle triangle also, we can conclude that the distance between negative x comma negative y and the origin will be equal to square root of x squared plus y squared. Now that we have proved the first part, which is the distances are equal, the conclusion that the distances are equal, the conclusion is that g of x divides f of x into two symmetric halves. Let's go to the figure. Why do we see this? Because g of x here, x comma y, doesn't have to be at this point. It could be further away, or it could be closer to the origin. And same thing for negative x comma negative y. Since the absolute value of x and the absolute value of y are the same, then we can consider g of x to be just as a mirror, and x comma y just as an object, and its image is negative x comma negative y. We know that wherever x comma y moves along tracing f of x in the first quarter, wherever it is, then negative x negative y will be, along with x comma y, equidistant from g of x. That is, if x comma y moves away further, negative x negative y will move away further by the same distance. If x comma y came closer to the origin, then negative x negative y will also come closer to the origin by the same distance. In the end, any move along this line f of x in the first quarter will be matched by a move in the third quarter by negative x negative y, and in the end both will be equidistant from g of x. So that is the proof that g of x will bisect f of x into two symmetric halves. And if that is the case, then the function f of x is indeed an odd function. To prove the function f of x as an odd function, let's just use this representation. We have x and y. Y is equal to f of x. So f of x is equal to y. And also we have here negative x, negative y. So f of negative x equal to negative y. So that means f of x equal to y and f of negative x equal to negative y. So let's go back to the proof. We said f of x equal to y, f of negative x equal to negative y. If we multiply f of x by negative 1 and y by negative 1, then we will have what? Negative f of x equal to negative y. And we have f of negative x equal to negative y. So if we have this negative y and this negative y, then negative f of x must be equal to f of negative x. We could do it in another way. Since we have f of negative x equal to negative y, we just repeat it over here. F of negative x equal to negative y. Now we want to see what is the equivalent of negative y. But not from this function, from this function. Equivalent of negative y is negative f of x. So we'll say negative y equal to negative f of x. So that means f of negative x ultimately equal to negative f of x for all x's. And that proves that f of x is indeed an odd function because it passed the test for the odd function. Now let's go ahead and prove that g of x is also an odd function. We're not going to take that long route to prove g of x. We're going to take a shortcut to prove g of x. Now g of x is this line. So this line, we're going to go ahead and assume g of negative x will be equal to y. g of negative x will be equal to y. So let's go ahead and report g of negative x equal to y. Also, if we look at this point, g of x equal to negative y. So we'll go ahead and report g of x is equal to negative y. Since g of x is equal to negative y, if we multiply both sides by negative 1, this will become negative g of x. This will become negative y, which is going to be positive y. So negative g of x, positive y. So this implies negative g of x is equal to positive y. The difference between this equality and this equality is just this equality multiplied by negative 1 on both sides will give us this. But then this equality, we can have y on the right hand side and there is y on the right hand side. That means the left hand side must be equal. So g of negative x must be equal to negative g of x. And since that is possible for all the values, because if we pull negative xy away from the origin as an object and this as the mirror, then its image will also pulled away by the same distance and the same logic that we used before. So regardless of where negative x comma negative y are, they will be all the time equidistant. So that means f of x divides g of x into two symmetric parts, and that proves that g of x is indeed an odd function, and we proved it by this logic. So we could just go ahead and get the conclusion here. G of negative x equal to negative g of x. We could also prove, but that's not something that I want to do. But anyway, if we could just change the places, we can just change the locations of g of x function and f of x function by rotation. But that doesn't really, so that rotation, the end of this rotation, now this was on this side representing g of x and this was on this side representing f of x, but it's okay. We have the theoretical proof there, so we're quite satisfied with that one. So let's go ahead and do the last part, the third part, which is we're going to use these two functions, f of x and g of x, to prove a nonlinear function, which will be h of x, to prove or disprove if it is odd function or not. Here is the hypothesis. Let the points x comma y and negative x comma negative y define a line f of x equal to x. If f of x is perpendicular to and symmetric about the line d of x equal to negative x for all values of x in the domain of a nonlinear function h of x, then h of x is an odd function. That is, h of x satisfies the condition h of negative x equal to negative h of x for every x in the domain shared by the three functions. Let's go ahead and, I know that this is a little bit verbose, but we will go ahead and prove this theorem step by step. So let's go ahead and take a look at the plotting. We have the plotting of f of x, the plotting of g of x. We're also going to place the function. This is h of x. This is a function. Actually, this is a representation of the function f of x equal to x cubed, x to the power 3. This is the representation of it, but we're going to demonstrate it anyway. Our proof, we're just going to proceed by the same. So this is just a repetition, sorry about that. This is a repetition to prove that f of x is actually an odd function. So first we did the slope, and then we argued that the function passes through the origin, and then after that we also talked about the distance. But before that, what we see here, we see this line spinning, and the spinning of this line, we're going to be talking about it in a minute. Let's just go ahead and finish this proof, and then we will go back to it. The distances, as we said, we already proved this one, so we're not going to go ahead and continue on this one, but let's go to the last point here. We want to prove that the function h of x is symmetric about g of x. The function f of x is the nonlinear. We want to prove it that it's symmetric about g of x. It's actually symmetric about g of x, and also it's symmetric about f of x, but we're not going to go through the symmetry about f of x. We'll just concentrate on symmetry about g of x. If we're able to prove one point that lies on the nonlinear function, this point x comma y is a point that is a solution of the nonlinear function, and its image also is a solution of a nonlinear function. So since they both lie on the curve of the nonlinear function, or on the plotting of the nonlinear function, or the graph, both of them lie on the graph, then we conclude that both of them are equidistant from g of x, because both of them are equidistant from g of x based on the fact that they are also points in f of x. So that's enough for us to prove that they prove that h of x, which is the nonlinear function, is also odd function. Let's go ahead and wrap this one up. So we're going to go ahead and just get h of x equal to y and h of negative x equal to negative y by the same logic, since h of x equal to y implies negative h of x equal to negative y. Now the right hand sides are negative y's. That means the left hand side must be equal for all x's and for all y's, and that indicates that this function is indeed an odd function. And it's true, this is an odd function because this represents f of x equal to x cubed, and x cubed does not have any term for x that's even, and at the same time it does not have any constant value. So let's go ahead and wrap this one up, and this is our conclusion: h of negative x equal to negative h of x for all values of x. We will go ahead and get the last part. The last part is generalization. We're going to go ahead and generalize the formula for nonlinear odd functions. We will start with a polynomial. F of x will be equal to a sub n x to the power n plus a sub n minus 1 x to the power n minus 1 plus all the way until a sub 2 x to the power 2 plus a sub 1 x to the power 1 plus a sub 0. Now we have this function. We're going to go ahead and extract from it a general formula for an odd function. So here is the condition for an odd function. The function f of x is an odd function if and only if the exponent for its variable x is odd for each term and there is no constant term. So if we look at the general formula for this polynomial, it has a constant term. This constant term should not be there if f of x has to represent a function that is odd. At the same time, if we find any term that has an x with exponent that's even, then the coefficient corresponding to that x with even exponent must be equal to 0, because we want to eliminate all the terms that have x with an exponent that's even. So if we put this restriction, the coefficient of every x with exponent that's even must be equal to 0. That means we will kill all the terms with x's having an even exponent. We will only be left with terms with x's that have odd exponents and no constant, and that's the only condition for the function to be an odd function. Let's go ahead and take examples. The first example, we have f of x equal to 2x to the power 4 plus 3x to the power 2. This is not an odd function. We can verify it mathematically, but we can also verify it by inspection. Since x has 4 and 4 is an exponent that's even, and the other x has 2 as exponent that's also even, so this function can never be an odd function. It must be, it's not an odd function. And if you do the math, we will get it. It's not an odd function. We can follow this one. So that's the reason written there. Let's take a look at the second example. F of x equal to 2x to the power 5 plus 3x to the power 3 plus 7. If we do the math, for example, take f of 1. So if we take f of 1, f of 1 will be equal to 1, f of 1 will be equal to 2 times 1 to the power 5, which is 2, plus 3 times 1 to the power 3, which is 3, plus 7, and that's going to give us 12. and we're going to go ahead and plug minus 1. So f of minus 1 will be equal to 2 times minus 1 to the power 5, which is minus 2, plus 3 times 1 to the power 3, which will give us minus 3, plus 7, that's going to give us minus 5 plus 7, which is plus 2. These two are not equal, so these left hand sides will not be equal no matter what. So this is also not an odd function for the simple reason it has a constant value, a constant term. Let's take a look at the last one. So the last one, the function f of x equal to 2 x to the power 5 plus 3 x to the power 7. First of all, there is no constant term. That's the good news. Second, there is no term with an x having an even exponent. So this must be an odd function, and we can verify that by plugging. We can verify that it is indeed an even function. And if it is good for one value, because we just plug, if it's good for one value, it's good for all the values. And this does not apply to this one only, it also applies to this function, which what we said, this function over here, we said since x comma y is shared between the nonlinear function and also the linear function f of x, and we prove that x comma y is equidistant. X comma y and negative x comma negative y are equidistant from g of x. Then they are also solutions to the nonlinear function, and they are part of the nonlinear function. So we prove that these are the same, equidistant from the g of x with respect to the function h of x. Then h of x itself is a function that is odd. We just need to prove one of them, just like what we did. What we did over here, we just used one value to prove that this is an odd function. This is an odd function. That's it for now. Thank you for following with this video, and we hope you enjoyed it. We will go ahead and do a follow-up video for the other two options for the theorem. You have a great day, and thank you for watching. Please subscribe for the channel.